the algorithms, learning bridge algorithms, transparent bridge. The packets are called DPDU. So everything has bridge in it because that's when it was the technology was created, early 80s, late 70s, early 80s. And so whenever you configure something, you're dealing with bridge. But now the word LAN switch has taken over, or Ethernet switch. Yeah, that's what is now commonly used. And it's a good thing that people don't use the bridge anymore. It actually can be a little bit confusing. There used to be devices that, there was the router back then, there was the bridge, and there was this, today it would be called layer 2 and 3 switches. That's essentially a router that can also do LAN switching. Essentially what in lab 6 we're going to use the Cisco routers exactly is both a LAN switch as well as a router. So they have both functionalities. There were devices sold in the mid-80s that were called routers. Routers. Router, bridge, router. So fortunately, that is also known. That term does not exist anymore. So we have to deal with this, and it's the reason that I'm calling it the term bridges. Before I get into it, I just want to talk in general about interconnection devices. What interconnection devices? You have different kinds of networks, and there's a device that connects them. Yeah, and so there's a whole array of different kind of devices that you can have. A hub, a bridge, a router, and there's something called a gateway. Different meaning than default gateway. And so what it means is they will all operate at different layers. You have interconnection devices at the MAC layer, so the lower part of the data link layer. You have interconnection devices at the data link layer. You have interconnection devices at the network layer, and then you have actually a gateway is a term for an interconnection device that connects two different kinds of network layer protocols. So if you're connecting something like an internet, a routed network to an X25 network, a different switching technology, and you would have a gateway. This, because everything is internet now, the gateway is no longer an issue. All right, so let's first look at hubs. So hubs are essentially, they connect Ethernet segments, or create Ethernet segments, connect Ethernet LANs, or connect multiple Ethernet LANs. And what they do is they generally, if you have collisions on an Ethernet hub would propagate that collision. That essentially creates out of multiple hubs a single hub. They operate the same way. Bridges are they're the same thing as routers, just routing functionality pushed down to the data link layer. So in the same, what we had before, let's look at routers maybe first. When we look at routers, this is our picture of the router world. The IP router has interfaces, data link layers, and then there is here this layer that performs the forwarding and has the routing table lookup. So a bridge or a LAN switch is the same thing. It just does this lookup. It has a lookup table in layer 2. It's a forwarding table, something like a routing table at that layer. And what makes things a little bit tricky is normally you have LAN switching, bridging, as well as routing taking place at the same time. Yeah? While there's forwarding rules here and forwarding rules in the routing table, so they operate at the same time, you have to know, you need some insight to understand how things should be configured and to determine why things take the path they take. So that's it. So the LAN switch is a device that interconnects two or more local area networks. They can be local area networks using a different technology. So here it's an 802.5 MAC, which is token ring, and here 802.3 is an Ethernet network. Today, essentially two types of local area networks, Wi-Fi and Ethernet. There's no more open ring. There's not a lot of variety out there. Wi-Fi would be 802.11. Yeah? All right. So the terminology I just explained. The term bridge came up when interconnection of local area networks, when devices were created that connected local area networks. So that's the term bridge. Today, LAN switch, or if you're talking Ethernet switch is the common term. But since the concept, protocols, and configuration commands for LAN switches, they were all developed in the 80s. Whenever you have these configuration commands, like in iOS, you use the term bridge appears. Yeah? So I also use both terms then interchangeably. So let's see, there's something here about the difference between the hub and the switch. We already discussed it. Yeah? So a switch at the level of just what the interconnect does is that a switch is really a packet switch that does buffering and has some backplane. A hub does not necessarily have buffering. So when two links transmit at the same time, you experience a collision. That is one difference between a hub and a switch. For our purposes, a switch also has a routing table. A switch also has a routing table, makes a lookup, and possibly runs a routing protocol. That's a protocol we call the spanning tree algorithm. Quite a beautiful algorithm, simple and beautiful. All right, so there are hubs, there are switches. They are buffered hubs. Yeah. They are dual speed hubs. Why don't we do that? It's just really great. So this is then a router. A router interconnects IP networks at the network layer. At the network layer. That's how we know this picture, and pretty much we know how this works. Gateways. So the term gateway is used in different contexts with a very different meaning. One term is that gateway is a generic term for routers, layer 3 interconnection devices. That's for the default gateway, the gateway of last resort. In that context, gateway is a router. But there's another context where gateway refers to devices that interconnect different layer 3 networks. You have in here SMA, System Network Architecture. That was IBM's packet switch architecture. So there was the Internet Protocol architecture. IBM had its own protocol architecture. DEC Digital had its own. DEC Digital Equipment Corporation had its own internet architecture. Xerox had one. So there were many architectures that existed. They have all fallen by the wayside. They're not really used. X25 may still exist, but this is just very, very old equipment, legacy equipment. In fact, I would not be surprised if our routers in the design center, possibly they support. I don't think they support X25. All right, so it's not just historic. Anyway, so with bridges versus routers, so we have, this world here, of having routers. You understand how we would know how to build a network. You have a local area networks on a floor, and you're having a router that connects to different local area networks. You have routers then that do routing internally on the campus, when they connect to an external router that then connects to other autonomous systems. You understand that? So, you know, why does one do routing also at the data link layer? And so that's kind of essentially a cost issue, and it's there for historic reasons. So it actually turned out that, you know, in the 80s, the example was really this, that campus networks or enterprise networks had bus local area networks which then terminated, and this would be like for one floor of an office building, you would have a local area network, and then you would have a router. This subnet would then connect somewhere in the basement into a router, so that in each building you had a router, and then there was a higher speed network. And what was popular in the late 80s, early 1990s was a fiber optic token bus network called the FDDI ring, operating at the blazing speed of 100 megabit per second. And the FDDI would then kind of provide the campus stuff. So today, campus networks look more like this, that you have switches all over, that the campus network itself is just run by Ethernet switches. That kind of pretty much the wiring, you have the wiring, here we have where is here our connection here. The wire going somewhere. Nope. How does it get it connected? Yeah. It cannot connect somewhere into a plug in the wall, which then goes to a switching cabinet. In that switching cabinet, you have Ethernet switch. That Ethernet switch connects to other Ethernet switches, and the backbone network of the campus is then operated by higher speed 10 gigabit switches or what have you. So, saying this is kind of how the routed enterprise network looks like. Typical for the early 90s, you have here your hubs connecting to a router, and then the backbone of the enterprise was then a high-speed network, which was essentially routed. Just routed. And then one of the routers connects to the internet. Then in the mid-90s, Ethernet switches became very cheap and very affordable, so pretty much the hubs were replaced by lower speed Ethernet switches. Which are not very different from the switches you buy from Linksys with 8 ports, just that the one in an office building has something like 48 ports. Otherwise, that's the normal density. You have a lower speed here, and then the backbone of the network is higher speed switches. Yeah, so first was 100 megabits here, and then a gigabit here, then you have a gigabit here, and a 10 gigabit on the backbone there. And probably very soon you get 100 gigabit Ethernet backbone. And then you have a router only to connect to the outside. So you could run an enterprise network completely based on Ethernet switches. So what we have today is a mix of both. So Toronto has roughly 30 routers, very small number of routers, but probably hundreds and hundreds, I would say, estimate somewhere between, somewhere between 700 to 1,000 Ethernet switches, probably, yeah? Mostly switched. All right. Yeah, so the difference between routers and switches. So why do people use? Why don't they want to use routers? Well, there's a class like this. Yeah, the class here, internetworking, is essentially a course so that you understand how to engineer an IP network. Essentially, a class on how to do IP. You need a whole semester course on that. There's no such class for Ethernet. For LAN switches, there's no course. There's nothing to do, nothing to learn. You plug things together. It just becomes complicated if you have Ethernet switches that work together with routers. Then you need to come back to this class. Yeah. You know, so for routers, yeah, you put an interface. You need to configure the interface. The interface needs to be configured consistently with subnet maps. You know, if the network is rearranged, move from one device from over here to over there, I take this computer, I move it into the band center, I have to reconfigure in all likelihood the IP address. Then the routing has to be done by the RIP or OSPF, has to be configured. And then as far as processing is concerned, for each packet that is being processed, the router has to inspect the header, do a check on the checksum, reduce the TTL field, recompute the checksum, send the packet out. There's a lot of processing that takes place on a header. Now, it's either with LAN switches, none of that really is an issue. Yeah? The addresses on a LAN switch are MAC addresses. The MAC addresses are hardwired. When you're buying your computer, it has the MAC addresses already in it. Nothing to configure. You move your computer to a different address. No, the MAC address does not change. It's always the same. Then you have it on the back. There's no network configuration needed. When you configure an Ethernet hub, and an Ethernet switch, you just plug in. And you've never really thought about thinking about a subnet map when you put your when you set up your when you plug into an Ethernet switch. And the routing, and you will see that the routing is also happening almost by magic. Yeah? There's nothing really to be set up or configured. Routers set up their routing table by the sniffing traffic. Let's see how that works. And lastly, for processing, while IP routers process the header, bridges, Ethernet switches, they do not manipulate the header. There's not so much to manipulate. Yeah, if you're having 14 bytes, source address, destination address, and the type field, there's nothing happening. So it's relatively easy to work with. Which then also the reduced complexity reduces cost, and so you can get these devices built and cheaper. Now, so what bridges or LAN switches give you is the concept of transparency. That was the term, the transparent bridge. Transparent in the sense of everything, configuration as well as routing, happens without any manual input. Plug and play. Network self-configure. I don't need to configure the address. All devices have their address. Bridges should not impact seven hardware software changes. Bridges should not impact operation of existing LAN. So you can just take switches, take them apart, move the switch somewhere else. Nothing needs to be done. So to understand how LAN switches work, I break this up in three pieces. This one piece is the forwarding of data frames. What's done, what's the equivalent of the routing table lookup in the IP module? How do routing tables get populated? Then there's the second, the second one, the learning of addresses. How do routing tables get populated? And the third one is the spanning tree algorithm. That is an algorithm that avoids loops in a topology. Alright, so let's go through this. So this is a typical picture here that you have. So the way to think about this is that this bridge is a device. Bridge number 2 is connected to 3 different LANs, and hosts are connected to LANs. Yeah, that's one way to think about this. So you have now different local area networks interconnected by bridges. Yeah? So what I'm talking about is how bridges accomplish this task. So let's see, this one here, yeah, they're different routing schemes really, but kind of what we discuss is the only one that is really in use today, the spanning tree routing, spanning tree routing protocol. This is standardized in IEEE 802.1d. Now that's the spanning tree algorithms. And bridges that run the spanning tree algorithm, they're called transparent bridges. All right, so let's look at forwarding. Forwarding is packet comes in, make a lookup, you determine which output port packet goes out to. So each bridge has a MAC forwarding table, which looks like this. It's like a routing table. The routing table, there's no structure, there's no concept of a LAN network or a network address. The address space is flat and has only MAC addresses. And the MAC address is the address of a device, like your Ethernet port or your Wi-Fi port. Then the next column is the outgoing port, and the third column is the age of the entry. So you read an entry like this. If a packet comes in with this destination address, you send the packet out on port 1, and this entry here is 10 seconds old. The reason that there's an H entry is that it's using soft state algorithms. State information that is old will eventually be deleted. Got a question?
This is different from CITR addresses because the MAC addresses are all easy, so the address is very, very long.
Very good. Yes, absolutely. The address can get very long. That's completely right. So what does it mean? What's the implication? Lookup is flat, yeah. Flat lookup, so it takes a long time to look up. It means that the scope, yeah, and what you have is not only is it flat, it's also end host, based on the end system. This computer here, if it receives a packet, this computer creates a routing table entry on each switch that it touches for each end system. Yeah? So which means that you probably cannot run a nationwide network with Ethernet switches. Yeah? So the question then, the scope of this is you need to be able to manage this. A couple of thousand, probably you can manage it. A million, probably not. Yes, good point. So these are the meaning of the entries, the MAC address, the port, and the age, and the interpretation is an entry of this form. A machine with this MAC address lies in the direction of port number this, and the entry has this time here. Okay, so that's the lookup. Now, what is now interesting is, and that's a big difference between a switch and a router. It's what's happening is if you have a packet, you look up the destination address and you don't find a match in the routing table. There's no match. And in the IP router, if there's no match, that means there's not even a default gateway configuration. There's no match for a packet, the router drops the packet. We know, yeah? Drops the packet. And a switch works completely different. If it has a packet and doesn't know what to do with it, it sends it out on all ports. It broadcasts. Which means you're turning your device on first time. If your routing table if you're sending packets out for the first time, if you're sending a packet for the first time, it will be broadcast in the entire switch network. And what's the scope of this broadcast? Well, it will go through all the switch network until it hits the router. Yeah, so that's the scope. That's it. It creates. So if you have another difference, if you want a flat routing table, it's a disadvantage. Another disadvantage is broadcast traffic. So this is described here. So assume a MAC arrives on port. So this is a bridge here with 4 ports. Let's suppose something arrives on port number X. Now it makes a lookup. The bridge is the MAC address of destination. Is MAC address of the destination in the forwarding table for port ABC. If it does not find, if it finds an entry, of course, it forwards the packet on the port. Yeah. I find an entry. Well, there's a port number. I forward it. If there is no entry, if no entry is found, then the frame is sent out on all ports except where the data came in. Yeah. You don't send it. You don't echo it back. That's how it works. It's completely simple. All right. Next piece is now, and this then comes together with the learning algorithms. So the routing tables get populated to a large extent by sniffing traffic, meaning you observe a switch observes traffic as it comes by, uses the information of each packet to set up a routing table. Let's see. And this one is called address learning. And bridges that do this, they're called learning bridges. So what I'm showing here is also called the learning bridge algorithm. But it's so simple, you don't have to, I avoid the term algorithm. So this is a switch with 6 ports. Let's suppose we're sending a packet. We're sending a packet to a switch that has just been plugged in. It has a source MAC address of X and destination address of Y. The routing table is entry. The routing table is empty. So what does the switch do? It sends the packet out on all ports. But then it says, well, I can learn something from this packet. This packet here came in on port number 3, so somehow I'm able to reach this address. I must be able to reach this address X by sending something out of port 3. So you're learning the entry. X, the destination address, the address X can be reached at port number 3. Then the packet is broadcast. So now let's suppose now that packets reply. This packet here that was sent on port 3 gets a reply from destination Y, and I think it's coming back on port number 4. So now the reply arrives at this particular switch. Well, this packet here, there's 2 things that take place. The switch looks up and says, well, the source address Y, this packet is coming from Y, well, I can make a new forwarding entry saying Y can be reached at port number 4, and then, well, I don't need to, there's no more broadcasting that takes place because the destination, for the destination Y, for the destination X, it already has a forwarding entry. Yeah, it has already learned something. So that's how it goes. Yeah, sends it out, no broadcast. Then the next packet comes from X at this point. For this purpose, the tables are initiated, yeah, and in this way, no more broadcasting takes place. So you see that the broadcast is only an issue. It helps, the broadcasting, number 1, helps to populate the routing table. Number 2, as soon as you're having a response coming back, the routing tables are established and broadcast, therefore, is a non-issue. Okay? All right, yes?
So I'm just wondering if in that case, if you are purposely sending a lot of packets with MAC address doesn't exist in this network, then you'd be able just to plot the entire network and bring down the network? Because everybody will broadcast, but the address doesn't exist, so no one will reply.
Well, I mean, if you're sending, let's suppose that you're sending a lot of packets to a non-existing host. Yeah? So this first packet here, yeah? Now this packet here, if destination Y is not on the network, that packet will always be broadcast. Actually, Y has to terminate. The reply pretty much puts an end to the broadcast. Yeah?
So that would be an issue, right? You want to destroy the network.
I mean, yeah. You know, in the end, if you're sending a lot of traffic to something that doesn't exist, you have to ask yourself, why am I doing this?
Right, but maybe you're just maliciously attacking something, I guess.
As a way of attack, sure. Yeah, I mean, you see, I mean, in large switch networks, you see a lot of broadcast traffic floating. So, yeah. You know, normally you're sending something, somebody replies and cancels it, but it's an issue, yeah. So the size, and then how do you contain this? When you contain it by, you know, route. If you're just defining, if you can limit the size of the switch network by just making it a subnet and interconnecting subnets by routers. Yeah, so you just make a switch environment that is large enough so it can be supported, and then you connect them by routers. And that's essentially what is done today in enterprise networks, or campus networks. Yeah.
So let's say you're doing broadcast and port 5 and port 6 are both connected to destination 1. So you just choose one.
Okay, well, very good. This, yeah, so by broadcasting, you have multiple connections. You can create misleading entries. That's, so what is, let's see, it can create problems, what you're describing. That's what is being solved by the spanning tree algorithm. In particular, what you can have is that loops can occur. That is what the spanning tree algorithm prevents. Very, very good. All right, so got this, the learning. It's actually not so, it's fun. It's just easy, could not make it. In the early 80s, actually, there were some national networks, or mid-80s, I should say, mid-80s, there were some national networks that were built based on bridges, based on land switches. Like Norway had a network that interconnected the research universities, and that was based on bridges. Okay. Yeah. Got this. So the learning algorithm is for each frame received, the source, not the source, the switch stores the source field in the forwarding database together with the port where the frame was received, and all entries are deleted after some time. This is important, yeah? If you're changing the connection from one, if this one here is a connection into an RJ45 cable, you're now reconnecting the same computer at on a different port, then you may have there's a timeout value of 50 that's relatively short, so that if this reconfiguration happens, that the switches react relatively quickly. Okay. So I have an example here, but it's a little bit difficult to do this. So we have this example here where we have this example here where we have 3 packets from A to F, from C to A, and from E to C. And just to see how quick this learning algorithm works. So when A sends something to F, the packet here reaches port 1 of the bridge. The routing table then says, the bridge then says, okay, I can reach A on port 1. It did not have a routing table, it doesn't have a routing table for destination F, so it sends the packet out over here. then sent on LAN 2, arrives on bridge number 2, which also an entry is created for the source address of the packet. Then the packet is sent out on port number 2 and reaches F. That's the first packet. We're done with this. Let's look at the second packet. So C is now sending a packet from C to A, bridge number 2 and let's see, one of them should be bridge number 1. Yeah, bridge number 1 and bridge number 2 both say, well, C can be reached on port 2, and bridge number 2 says bridge port C can be reached on port 1. Then the packet is forwarded here by bridge 1 onto port 1 and reaches A. So then when E sends a packet to C, so the bridge number 2 sets up a routing table entry for E on port 2. Then A is being sent, let's see, the packet is being sent out destination C on port 1, where the packet is then forwarded, reaches then the destination. Yeah, so that's essentially how the learning algorithm works. And C does not forward the packet because it knows that C is, it does not forward the packet onto this port because it has already a routing table. That's it. What is open is what we have not discussed is that if you have the learning algorithm, and that's what you alluded to, what can happen is that loops can happen, and loops are avoided by organizing the local area network in a tree topology, and only use bridges that are part of the tree, and never forward packets along edges that are not part of the tree. A tree does not have loops. So if you're setting up a tree like this and you only forward traffic on the edges of the tree, along the edges of the tree, loops are avoided. The standard tree algorithm is something very important, not that hard, but it's you need to think about it a little bit. We'll discuss that tomorrow morning. Is that good? All right. Thank you. See you tomorrow morning. Yeah.
所以我们的考试是下周3了，改成。
Oh yeah, so this is exactly the scenario here when things happen at the same time.
对啊，要不然太屎了。我跟他就说周2考试太多了。